Good morning everyone and welcome to the Physics Optional 2026 course. First of all, congratulations on choosing Physics as your optional, a decision that reflects not just courage but also clarity. Physics may not be the easiest subject in the UPSC sphere, but it is undoubtedly one of the most rewarding both in terms of scoring potential and intellectual satisfaction. This course has been months in the making, structured, refined and polished with inputs from the top scorers and persistent aspirants like yourself. Our goal is simple: to help you to master the subject, and not just for the exam but with genuine conceptual clarity. Every video, every note, every problem set is purpose built to keep you focused, motivated and UPSC ready. We will be covering both paper 1 and paper 2 comprehensively with detailed notes, problem solving techniques, previous year question discussions and ongoing mentorship to keep you on track. And today we begin with quantum mechanics, a subject that often intimidates students, but I assure you by the end of this module you will not only understand it, you will enjoy it. So let's begin this journey with energy and curiosity. This isn't just about cracking an exam, it's also about building a solid understanding of the subject that explains the very basic fabric of the reality. So let's dive in. So first chapter that we are going to study is the origin of the quantum mechanics. So here we are going to study three great topics. The first topic is black body radiation. The first topic is black body radiation. The second topic is photoelectric effect, and the third topic is Compton effect. And let me tell you very clearly that these all are nothing but particle manifestation of radiation. This is particle manifestation of radiation. So in one simple language, we could say that black body radiation, photoelectric effect and Compton effect are nothing but particle manifestation of radiation. So let's move forward. The first chapter is from our module of quantum mechanics is the origin of quantum mechanics itself. And we are going to study black body radiation and Planck's quantum hypothesis. So black body, its study led to beginning of the conceptual fabrication of quantum mechanics. We will see how. And what is black body? So any object which absorbs all the radiation thrown on it is called black body. Additionally, I would like to clarify that on the in the thermal equilibrium, it not only absorbs but also emits all the radiation. Emits all the radiation thrown on it. So also let me clarify you that there is no ideal black body in real. No ideal black body do exist in real. So we will start with its closest approximation. So closest approximation is a hollow enclosure which has a small entrance hole for the radiation to come inside and the blackened inner walls for the successive reflection, so that all the energy gets absorbed. Blackened inner wall for what? Successive reflection. So it enters here from here and then it goes on to successive reflection till all the energy, successive reflections, till all the energy of radiation gets absorbed. This is what we call black body. So first thing what we did, that we observed the spectrum emitted by black body. A spectrum means the range of the wavelengths and the intensity corresponding to those. So here we could see that in figure 1 we have the spectral distribution of radiation from a black body, and we need to observe that radiated energy on this curve is maximum at a particular wavelength. So this is the intensity versus wavelength curve, and intensity is obviously a dependent of the wavelength. So it depicts the original spectrum as emitted by the black body. Such black body, approximate black body, not the ideal one. Hence, many theorists were interested in this particular development, and they tried to explain the emitted spectrum through the theory. They tried to explain it through the theory. Okay. So, if I tell you, some prominent theorists of such were, some prominent theories given by such theorists were Wien's law, Rayleigh-Jeans law, and Planck's radiation law. So these are in the successive manner. So at first Wien's law was developed, then Rayleigh-Jeans law, then finally Planck's law. So we are going to study these all, and these all are the part of the PYQ. So we are studying something new, and at the same time we are also solving the associated PYQ with this topic. So what is Wien's law? So Wien's law, while devising this particular law, the theorist used the thermodynamics, dimensional analysis, and some scaling argument. Scaling arguments mean using the constants. So it is a kind of semi-empirical formula. So what he proposed that intensity as a function of wavelength is inversely proportional to lambda to the power 5, and it is directly proportional to exponential minus b divided by lambda upon t. And we know that this lambda is wavelength and this t is temperature. And this constant a and b are decided empirically. So that is why we call it semi-empirical kind of formula. So what happened that such law fit the observed curve well, but they failed at the longer wavelength. So what happens? So suppose that if you plot the curve, this curve will be like this. So we know that whenever the wavelength is exceeding a certain limit, this curve is not matching the original curve. So this is a kind of failure at longer wavelength. Okay. Then we have another kind of semi-empirical formula, which is Rayleigh-Jeans law. So another kind of development on the semi-empirical formula, which is Rayleigh-Jeans law. And let me tell you why we call it semi-empirical, because it was not derived from known and from the Wien's law was not derived from the known and well-established theory. Okay, so we need to derive it from the known and well-established theory, so it has better agreement in the scientific world. So here very important argument that Wien's formula was semi-empirical and was not derived from the known and well-established theory. That is why we are proceeding with Rayleigh-Jeans law. Hence, next theory was given by Rayleigh-Jeans by two scientists, Rayleigh and Jeans, and which were based on the classical electrodynamics, and thermodynamics. So what they did a very interesting thing, that they assumed radiating body as collection of large number of charged particles. So what they hypothesized that radiating body is nothing but a collection of large number of charged particles. Okay, sensible. So what those kind of charged particles were doing? So the question is, what those charged particles are doing? The answer is very simple. They are performing linear harmonic oscillation. So what they used to do, that these oscillating charges do emit. Oscillations means doing something repeatedly in a kind of periodic fashion. So they were emitting and absorbing the electromagnetic radiation while they were maintaining the thermal equilibrium. So we could say that at thermal equilibrium, energy density of the radiation within the cavity. So we have this black body. So this is entrance, and inside this cavity there is radiation being repeatedly reflected and absorbed at the subsequent reflection. on the surface, because this is the basic nature of the interaction of radiation and matter, that whenever the radiation will strike at any surface, it will either get absorbed or reflected, something like that. So we could say that energy density of radiation within the cavity is equal to energy density of the atomic oscillator at the walls of the cavity. Okay, so great. So we know that this on this wall contains the atoms. Okay, and those atoms are in simple harmonic oscillation. What kind of simple harmonic oscillation? That at certain moment the first step is going like that. You electrons are there, they are gaining energy. While gaining energy, they are moving to next energy level, then they are releasing energy, and then they are coming back to the same energy level. So this particular movement, this particular oscillation is being repeated. That is why we have assumed that this is simple harmonic oscillator. So this was the hypothesis. Now let's move to the mathematical formulation. So what we are doing, that mathematically we discovered that number of such oscillators in a unit volume is a function of frequency of the radiation, and it is equal to 8 pi, and this formula is little bit of 8 pi nu square upon c cube. Just correct it. This is little bit wrong. Okay, and this mu is nothing but frequency. And for such setup, the average energy is given from the classical equipartition theorem, which you might have studied in thermodynamics. And it is equal to kT. Okay, hence energy density of radiation of the frequency is simply this total number multiplied with the average energy. Okay, and again I have written it wrong here, so let me correct you, that it is mu square and c cube. Okay, so energy directly proportional to the frequency, and it is k times t, so it is also directly proportional to the temperature. But what happened, this was also correct, but it failed at shorter wavelength. Wien's law was failing at longer wavelength, but this particular formulation is failing at shorter wavelength, and rest was fine, but it failed at shorter wavelength. So if you try to plot the Rayleigh-Jeans law, you would be plotting like this. Okay, and this particular plot is a Rayleigh-Jeans law plot. Also, if you move forward in the mathematical formulation, we could say that this formulation, that is Jeans a number which was initially written in the term of frequency, could be written in the term of lambda as well. Then we will do little bit of variation in its LHS and RHS, and we get that n as a function of wavelength is equal to n as a function of frequency and derivative of frequency with wavelength. So we know that frequency is nothing but it is c upon lambda. So we did the same thing here. We did the little bit of differentiation, and we finally find that the Jeans number in the form of wavelength is inversely proportional to the fourth power of the wavelength. So now let's move forward. Now in this manner, the energy density is nothing but 8 pi divided by lambda 4 multiplied by kT. Furthermore, what we find interesting, that intensity of radiation of the cavity is proportional to the energy density, and that is what it should be. Like more the energy, there should be better chances of intensity. So this is the mathematical logic. So when you try to find it exactly, it is actually intensity as a function of lambda is equal to c divided by 4 multiplied by energy density. Okay, so this is the exact relation. Okay, but in general, what do we write? That intensity is generally proportional to energy density. This is the generic information which you must know. And let me tell you one very important part, that this kind of argument in physics is a necessary argument which you must write in your answer to improve the quality. Okay. But let us find one very important thing, that energy cannot be infinite, or energy density cannot be infinite. But in this case, if you try to find the energy from all the frequency range, that is energy contained in a particular spectrum, then we find that energy is infinite. Let us see how. So, the main failure of such is that it leads to total energy in the frequency range from 0 to infinite. 0 to infinite is infinite. That is total energy density. To be honest, not total energy density. So we know that total energy density cannot be infinite, that too in the widest possible spectrum. Okay. So what you do, you just integrate it, and if you know that you are integrating the frequency square with respect to frequency itself, then we know that in the range 0 to infinity it is going to be infinity itself. And this is what we call ultraviolet catastrophe. Ultraviolet catastrophe. So the argument goes as follows. In any range of the frequency, there cannot be infinite energy density. Okay. There cannot be infinite energy density. And this issue was well known at that time as ultraviolet catastrophe, because they observed it in ultraviolet range at first. Okay. And the same concept has been asked as PYQ as well. Okay. So now let us just summarize some fundamental law of the Rayleigh-Jeans law. So energy goes to infinite, that is, it leads to ultraviolet catastrophe, or precisely I would like to write energy density. Energy density goes to infinite, and it is also known as ultraviolet catastrophe. And as this law was derived using the concepts from the classical mechanics, so its failure leads to conclusion that study or development of the classical physics is incomplete as of now. So we need to study it even more. Now we are done with the Rayleigh-Jeans law. Now let's move to the Planck's radiation law next. So to solve the underlying issue of the explanation of the spectrum as observed by black body, Planck assumed that material oscillator with walls of the cavity can only have the discrete energy. They cannot have the continuous energy. So till now we have known that the energy could be continuous. Okay. But this person, he proposed that energy cannot be continuous, it could be discrete only. That we are going to discover what exactly discrete means. So it is discrete rather than the continuous range of the energies, and if a particle is oscillating with frequency nu, then the energy can have the values which are integral multiple of h and nu. Okay, h is nothing but Planck's constant, and it is frequency, and it is integral multiple. Integral means 0, 1, 2, 3 and 4. So this is the generic form of energy, that is energy is equal to nh nu. Okay, and this is what we refer as quantization of energy. Okay. Now let me tell you very clearly, as energies are integral and not continuous, that means average energy now cannot be kT, which we derived from the classical equipartition theorem. Okay, average energy cannot be kT, and this has to be something else. So what it has to be, let us see. So what we are going to do, we are going to do the calculation of the average energy considering the quantization of energy. So consider all the particles are oscillating with frequency nu, and at absolute zero, at absolute zero, we understand that all the oscillators will have energy state as ground state. So they will be in the ground state themselves at absolute zero. But if you start raising the temperature, then some of the oscillators will jump to the excited state or higher energy levels. Okay, because if they gain energy, so they will gain the energy as well. So if they gain the energy, they will move upward in the energy level. Okay, this is first energy level, this is second energy level, this is third energy level. So this is what happens. So when you supply the energy, they will move to the higher energy level. But if they lose that particular energy, then they will come back to the lower energy level. So this is what happened. And this is something new. We have studied this particular concept in class 11th and in 12th as well. So, thus at temperature T, but in equilibrium, the number of oscillators with energy En. Suppose that there are n oscillators. Okay. So first oscillator will have energy E1, second will have energy E2, third will have E3, and so on. So we call it generally En. Okay. So the total number of such oscillators will be given by this particular relation. Okay. Which is n is equal to n naught multiplied by exponential minus En upon kt. Okay. And we have got this particular information from the Maxwell-Boltzmann statistics. So this writing such argument is very important because we are not deriving it. So we must state the source of the concept which we have used. And without this, you will not get marks if you write this plain information. So as per the equation 1, we can see that as n goes to infinity, the total number of the particles is going to 0. So let's see, it is negative exponential. So it is pretty destined to happen that if you increase the total number of particles to infinity, the n to be infinity, that is level of the energy level to be infinity, there would be 0 particles. That we know that at higher and higher energy levels, at higher and higher energy levels, number of particles keep reducing. I think if you know the concept from the statistical physics, there is one term called partition function, which says that probability of particles occupying higher and higher energy level keep reducing. Okay, so this is what we need to keep in mind. So we know that in such a case, we could conclude that higher energy level states are less likely to be populated in one simple sentence. But I have provided you the value addition as well, because enrichment is very necessary. We need to understand that in which part of the syllabus, which other part of the syllabus is connected. So this particular concept is connected from the Maxwell-Boltzmann statistics, which you are going to study in the thermal and statistical physics. Thermal and statistical physics. Okay. So now let us try to find the average energy, because earlier we had the average energy equal to kT from the classical equipartition theorem, but right now it is not correct because energy is quantized and it is not continuous. So it must change. That is our argument. So average energy per unit oscillator, that is per oscillator, is given by this particular form, where it is summation of n times the energy, okay, from the range n equals to 0 to n to infinity, and summation of n. Okay. So when you try to solve it, you substitute n equals to n naught exponential minus En upon kt, and this is this you derived from the Maxwell-Boltzmann statistics. Okay. So when you got it, you simply cancel all the terms and you finally go write that energy is equal to h nu divided by exponential h nu upon kt. Okay. So because you know that energy is quantized, so it is E h nu, and energy is equal to h nu, and this is where you got the energy term, h nu term, or the term of the quantization. Okay. So you might take the shortcut while deriving the complete formulation, but your start and end should be well formulated, and it should be in the proper directional flow. So that will tell your examiner that okay, this person has studied all the required concept well, and this person is only cutting shortcut in the mathematical derivation part and not in the expression part. Okay, so you could cut shortcut in derivation part by writing the argument, but you cannot cut shortcut in expressing the maths and arguing on it. So arguments are very necessary. So you must express your mathematical equations, formulations, whatever you want to do. You just argue on it, put the physical significance of it, write the physics around it, but you could take the shortcut around derivation where the derivation is explicitly not asked. So with this energy, average energy, we are going to write the renewed energy density inside the cavity, which is the Jeans number multiplied with the average energy. Okay, and this is what we have got. So average energy as a function of frequency and temperature is 8 pi mu square divided by CQ multiplied by the average energy. Okay, and this is nothing but the Planck's radiation law, and the beauty of this Planck's radiation law is that it fitted well everything. Okay, it passed the test of the spectral energy density curve. So this is what we had, the spectral energy density curve. So it passed the test. Okay, so that is why Planck's radiation law was accepted, and Planck's hypothesis was further used by Einstein to study the photoelectric effect. Okay, now if you write frequency is equal to c upon lambda, and you substitute this whole thing here, so you will get that energy density in the form of as a function of wavelength and temperature. So it is 8 pi hc divided by lambda to the power 5 equal to E hc divided by kt minus 1. Okay, and let me tell you very clearly that this law, so when the lambda shoots to 0, this law becomes Wien's law, and when lambda shoots to infinity, this law becomes Rayleigh-Jean's law. This is what we have studied, that Wien's law fails at longer wavelength. That means it passes at shorter wavelength. Okay, and vice versa for the same when lambda tends to infinity. So we are going to write the summary of the section 1, and I am going to provide you some homework as well from the book of quantum mechanics written by MC Jain. So summary of section 1 says that Wien's law is intensity as a function of lambda and t, and it is equal to a divided by lambda to the power 5 multiplied by exponential minus b upon kt, and it fails at longer wavelength. For Rayleigh-Jean's law, we are going to write energy density as a function of frequency and temperature, and it is 8 pi nu square upon c cube multiplied by kt, and it fails at shorter wavelength, and it leads to ultraviolet catastrophe. And then we have finally Planck's radiation law, the ultimate success, and it is function of frequency and temperature, but the average energy do have the different form. Okay, so it correctly fits the observed spectral curve. At lambda tending to 0, it becomes Wien's law. At lambda tending to infinity, it becomes Rayleigh-Jean's law. So this was the first topic which we completed today. Now we are going to complete the second topic. Okay, and let us meet in the second part of the. So welcome back. Now let's start with photoelectric effect. So when an electromagnetic wave or radiation of sufficiently high frequency hits at the metal surface, electrons are ejected out of that metal surface. Okay, and this effect was first observed by Heinrich Hertz in 1887. This was the simple setup which consists of emitter, incident radiation, collector plate, and the voltage source of the variable voltage, okay, and the ammeter to measure the current. So they performed this particular experiment, and then some observations were made. Some observations means exactly 4 observations, and these 4 observations were that there is minimum frequency required to get electron ejected, and it is termed as threshold frequency. The kinetic energy of electrons ejected do have a maximum value. Photoelectric effect or electron ejection is instantaneous process, and photoelectric current depends upon the intensity of the radiation and not on the frequency. So, and out of these 4 observations, only last observation could be explained by the classical physics, and rest were not explainable. So, the first 3 observations could only be explained by considering the quantum hypothesis. And this is what Einstein did. Okay, this is what Einstein did. So, let us try to understand the Einstein's theory, which is very interesting, and it led him towards the path of Nobel Prize. So, Einstein continued using the Planck's quantum hypothesis, and he explained incident radiation acts as a stream of bundles having energy h nu. Okay, and let me tell you clearly, these bundles are later on known as photons. So, when these bundles collide with the electrons within the metal, provided that the incident stream do have the minimum frequency mu naught, which is known as threshold frequency, So, the energy is transferred to electron, and electrons are ejected from the metal itself, and they constitute the photoelectric current, which has great application in solar cells. The solar cells are the application of the photoelectric effect. Now, we do have the minimum threshold frequency. Minimum frequency, which is called threshold frequency. So, if you throw the radiation of below this level, the electrons are not going to get ejected. And let me tell you very clearly that this threshold frequency is characteristic of metals. So, different metal, different minimum frequency required to get the metal ejected, and this is logical as well. So, the energy corresponding to this threshold frequency is known as work function, and it is necessary trade-off, that is to eject the electron, you must at first expend this much energy. So, suppose we are throwing the radiation of mu frequency, then this particular one single photon would have energy h nu. But from this h nu, we need to subtract the work function, that is energy corresponding to the threshold frequency. Then only the remaining energy is going to be used for the ejection of the electron. So, kinetic energy, that is motion of electron, would have the maximum description given by this Emax, that is maximum kinetic energy. And this is what we call Einstein's photoelectric effect, and this is maximum kinetic energy. Okay. And as I told you that this threshold frequency is characteristic of metal. Now let us try to understand the concept of stopping potential. So, if the collector plate is made negative, okay, so electron is also negative, and now collector plate is also negative, then photoelectrons will be repelled. Okay, and if the potential as such which is being applied is greater than the corresponding energy, then the photoelectric flow would stop. So, if you keep increasing the voltage, okay, this is the variable voltage. So, if you keep increasing it, so at one point of time, this will increase to such an extent that this electron will stop flowing. So, this is what we have termed or called stopping potential. Okay, so it will stop, and that potential is known as stopping potential. So, we know that work is equal to charge times potential. And this work at one point of time would be converted to energy or something like that, because we know that they are interrelated, that work is maximum amount of energy you can spend. So kinetic energy is basically charge multiplied with potential. So this is what we have written here, that EV0 is Emax, and we know that Emax is nothing but h nu. So we know h nu minus work function. So this is what we have got, that charge multiplied with applied potential, which is actually stopping the electron, by from flowing. So it is h nu minus work function. Okay. So EV0 equals to h nu minus HV0, and you are taking h common. So you are finally getting the stopping potential. This is stopping potential to be mu minus mu naught. Okay. So thus the theory as explained established the correctness of the quantum concept. Okay. And using the slope that is h upon E, Millikan found that a value of h is 6.626 multiplied with 10 to the power minus 34 joule second. Okay. And for the same work, for the work in the realm of explaining the photoelectric effect, Einstein got the Nobel Prize, and then in the work for the work to find the value of the h, that is Planck's constant, the Millikan got the Nobel Prize in 1923. So in the span of 2 years, they both got the Nobel Prize. So we know that this is the, and let me tell you, there is one small mistake, that this is not, this is S, stopping potential is Vs. So this is correct. Okay, and now we are fine. Okay, so Vs is stopping potential, and this mu naught is threshold frequency, TF, threshold frequency. So this is what we have studied till now. Now let's move to the next important topic, that is Compton effect. So in simple manner, in simple language, we could say that Compton effect is collision of wave and particle. Here wave is photon and particle is electron, and if not collision, then we call interaction definitely. So observation was that when X-rays are scattered using the atom having the low atomic energy, that is something like carbon, then obviously if you bring the X-rays on some such atom like carbon, then X-rays are going to get scattered, and then when they are scattered and when you observe, you will find that there are two intensity peaks. Okay, the first peak was observed at the incident wavelength itself. The first peak was observed at incident wavelength itself, and the next peak was at slightly longer than the incident wavelength. So this is what we have termed the Compton effect, and I know right now you would not have got what is special in this. Why we are observing? What is special in observation of the two intensity peak at two different wavelengths? Okay, so we are just going to clear it in next few moments. So this Compton effect, why it is powerful, that it provides the most direct evidence of the particle nature of radiation, and it was a kind of collision in between photon, which is particle, and electron. Okay, so because it is a kind of because photon is colliding with electron, we can term that it is a kind of particle. Okay, so it explains the duality. And more specifically, we can call it wave-particle duality. That means sometimes wave is particle and sometimes particle is wave. So if I tell you very clearly, so these are examples of waves are like particles. Okay. And why? Because we have studied the black body radiation. In second, we have studied the photoelectric effect, and in third, we are studying the Compton effect. And then in further chapters you are going to study like particles are wave. The converse of this, particles are wave. So I think if you remember the Breuer wavelength is one such topic. So now let's try to understand the experimental setup which leads to observation. So here we have the source of X-ray and then we have the collimator. Okay, and the source of the X-ray is monochromatic. That is, it is made of single color. Chromatic means color, and single color means single frequency. Single frequency. So single means mono, frequency means chromatic. So we call it monochromatic. And this is scattering material which is of light atomic weight. Scattering material, light atomic weight. And this is X-ray spectrometer which lets you observe the spectrum of the spectrum X-rays which are scattered by the scattering material. Okay, for example, carbon. So let me tell you very clearly that this Compton effect for some reason was not explained by classical physics. Classical physics failed to explain the Compton effect. Let us see why. This is very interesting. That why did classical mechanics could not explain the Compton effect? So let me explain this. That as per classical physics, an incoming electromagnetic waves drives the electron into SHM. Okay, so suppose that there are electrons. So whenever the electromagnetic waves strike as those electromagnetic electrons goes into SHM, and the electron then re-radiates. Suppose that the electron is in this energy level Q, then whenever you will throw the radiation on it, so it will move to E2. Okay, but once it have moved, it stays for very less time. It stays in excited state for very less time, and thus it comes back to the E1, and to come back it will have to shed off or leave the extra energy. Shed off or leave the extra energy, and leaving this extra energy will be in the form of radiation. So in simple language, it is going to re-radiate or scatter the radiation. So this is what we are calling scattering. So it will re-radiate the EM wave and X-ray in our case, and at the same frequency, because whatever it will absorb, the same it will emit as well. Okay, so at the same frequency or at the same wavelength as the incident wave. Okay, so we know that energy and momentum are carried continuously by the wave, that is, electron absorb and re-emit the X-rays with no net change in wavelength. Because whatever the electron, classically, we are talking classically. So whenever the electron is going to absorb some extra energy, it is going to get excited. Then, because it cannot be excited for a very long time, it will get back to its home or ground state energy or the whatever energy it was initially in, and to do that it will re-radiate the energy. So simply whatever you are going to provide it, the same it will re-radiate. So single wavelength. But in real, recall, we have observed two intensity peaks. One at incident wavelength. So it was explained by the classical physics. Explainable by classical physics. But what about this slightly longer wavelength? Cannot be explained. No answer. Cannot be explained by classical physics. So that is where we are again going to bring the quantum hypothesis. So we know that in real it was observed that the scattered X-rays had slightly longer wavelength too, apart from the no net change in the wavelength wala wavelength. Okay. So we are again going to bring down the quantum hypothesis, that is using the discrete energy packet to explain the Compton effect. So Compton used quantum theory, that is he assumed that X-rays are a stream of photons with with energy h nu, okay, and photons from X-ray are making elastic collision with the electron within the atom. That means we are going to use law of conservation of energy for this system and law of conservation of momentum for this system. So this is a typical setup for the collision, and we know that this is electron kept here initially, then incident photon strikes on it, and the scattered photons moves on angle theta, and this moves on angle psi. So let's move forward. So we know that we need to apply the conservation principles of energy and momentum. We are required to find initial and final condition. So energy and momentum of the incident photon are nothing but h nu and h nu upon c. So we know that for the particles such as photon, or for the entities such as photon, we have energy square is equal to p square c square plus rest mass energy square. For photon, this rest mass energy square is 0. So we are left with E square is equal to P square C square, or P is equal to E by C, or E is h nu, so P is equal to h nu by C. So this is what I have written. Now energy and momentum of a scattered photon are h nu prime and h nu prime upon C. So what will happen that initially the frequency of this photon is going to be nu. Then some of the energy will be transferred to electron and the frequency will change, so it will become mu prime. Okay, so this is the setup. So finally, when the collision happens, so energy will become h nu prime and it will become h nu prime upon C. The momentum will become h nu prime upon C. Now for electron, energy and momentum will be in m0 c square and 0. So we know that electron is at rest. Electron is at rest in our experiment. So that is why it is 0, and the energy momentum of energy is momentum of electron is 0 because it is at rest, and energy of the electron is its rest mass energy. Okay, which is rest mass energy of electron is nothing but m0 c square. Okay, and after the collision there will be subtle changes. So changes will be that energy of electron will be given by this particular expression, which is p square c square plus m0 c square square under root, and momentum will be some value p. Okay, what value we will find it by applying the conservation principles mathematically, but it will be some value p, let's say that, and we have used this particular expression. So now we are going to apply conservation of energy. So initial energy of the system is equal to final energy of the system. Energy is h nu plus m0 c square. Okay, h nu is for photon, it is for electron, and now the energy of the photon is h nu prime, and this is the energy for the electron, which we have described in this particular setup here. Now what you will do, you will also apply the conservation of momentum, and we know that momentum is a kind of vector quantity, so we will apply it in the y direction and then in x direction. So we know that in y direction there is no momentum for incident photon because photon is moving along x direction. This is x, this is y. So there is no momentum for photon in y direction. and electron is obviously at rest. So in both the direction there will be no momentum for electron. And once when there is collision, so we will find that momentum of the photon in the y direction after the collision is going to be h nu prime upon c into sin theta. So this is our theta. So we could know that this is h nu prime multiplied with sin theta. The same thing we are gonna write for electron, which is minus p sin phi, because this is going into negative y direction. Okay. So we are just breaking this into components using the class 11 vector mathematics. Okay. For the same could be done for the initial momentum and final momentum of the system along the x direction after the collision, before and after the collision. So we know that momentum of the photon is h nu by c in the x direction, and for the electron it is 0, and this quantity is for the photon and electron in the situation after the collision. So these are marked as equation 2, 3, and this equation is marked as equation 1. So we have 3 important relations, 1 for energy and 2 for momentum in the x and y direction. Now what we will do, we will square them and combine them. What? Equation 2 and equation 3. So whenever we square them and combine them, so we will notice that this also have cos theta term, this also have sin theta term, and the constants or coefficients are same. So whenever you square them and do things like that, they will simply get cancelled out, because square and p square sin square and cos square term sin square term will get 1 after summing it up. Okay, and you will have to manipulate something like that. And I have just okay, this is this terms. Okay, so by the simple mathematical manipulation, we have put this p square h square upon c square equals to this particular expression, okay, on the left hand side and right hand side. Now what we are going to do, we are going to solve the formulation given by this particular energy equation as well, and we will combine them. And when we will combine them, we will finally find that lambda prime minus lambda is equal to h upon m naught c multiplied by 1 minus cos theta. Okay. So what we will do, we have this p square h square upon c square. So we will go to equation 1. We will manipulate it in a way that we get the value of p square h square divided by c square. And once we do that, we are back with this particular expression where 2 m naught c square divided by h is equal to mu minus mu prime equals to 2 mu prime 1 minus cos theta. Okay. And then what you can do, you can just convert this 2 into this form, 1 upon mu prime minus mu, and this could be lambda prime minus lambda. Okay, because lambda is longer, so we have kept it at first, and this is what we are getting from the mathematical constants as well. So finally, lambda prime minus lambda is equal to h upon m naught c and multiplied by 1 minus cos theta whole bracket. Okay. So this is change in wavelength, which is given by lambda c multiplied by 1 minus cos theta. This lambda c we call the Compton wavelength. We call it Compton wavelength, and it is h upon m naught c. And if you calculate, try to calculate the Compton wavelength, that is 0.0242 angstrom. Now we are going to find the relationship in between this theta and psi. I think you could do it at your own, because you need to solve the equations only. In simple manner, you need to solve the equations only. So try to pause the video and do it yourself. This is very basic level of mathematical manipulation, but if you don't want to do it, let's move on. So from conservation of momentum, we already have PC by h PC upon h multiplied by cos theta and mu minus mu prime cos theta. PC by h sin theta equal to mu prime sin theta. This is what we have just used the conservation of momentum. Now we know that the left hand sides of equation 4 and equation 5 could be divided to get the tan theta term. So this is what we have done here. Okay. So when you divide equation 4 by equation 5, we get that these are getting cancelled, PC upon H, PC upon H, and cos psi divided by sin psi is nothing but cot psi. And here we have got some constant which is 1 plus alpha, and this is tan theta we do. And alpha is nothing but h nu upon rest mass energy. So alpha is a kind of constant because this is also a kind of energy, this is also a kind of energy. Okay. So this is what you have got, the relationship in between this and this. And let me tell you very clearly, this you will also study in mechanics. Why you will also study in mechanics? Because it is a kind of collision. And in collision, you are going to understand all the interrelationship in between the colliding particle in their center of mass frame of reference and in the observer's frame of reference. So these all are going to be not the alone topic which you will encounter here, but you will encounter it again, and precisely this all this particular topic is PYQ as well. Okay. So understand it deeply so that whatever topics questions are going to get framed in this, you could answer them pretty well. Now we are going to find the kinetic energy of the recoil electron. So what happens when the photon is incident photon is colliding with this electron is going to get recoiled in some particular direction at angle psi with respect to the incident direction. So we are going to find it. So we know that whatever the energy of the incident photon would be, and whatever the energy of the scattered photon would be, the difference of that will be only transferred to electron. So kinetic energy of electron would be simply the difference of the energies of the incident photon and the scattered photon. So when you simply subtract it, you will get h nu minus h nu prime. Okay, and h nu minus h, and for nu prime you could write this particular expression. Okay. You have used this by using the momentum conservation equation simply, and these all are very simple mathematical manipulation. Be confident this you used to do in class 11th and 12th. Okay, so never lose your mindset, never lose your confidence. This is what I would always suggest to you. So finally, the kinetic energy of electron is h nu multiplied by alpha, which is h nu upon m naught Ca square multiplied by 1 minus cos theta plus 1 plus alpha multiplied by 1 minus cos theta. Okay, and in term of psi, suppose here we have written it in the term of theta, in terms of psi you could write it like this, that is h nu 2 alpha cos square psi divided by 1 plus alpha whole square minus alpha square cos square phi, and to do that we have used this particular interrelation in between these all things. Okay, so